Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS WxTalk Webinars. Thank you for joining us today. I'm your host, Henry Regis, and running the technical side of our program is our own Noah Newman. Also joining me today is CoCoRaHS founder Nolan Duskin. We're coming to you live from the Colorado Climate Center here in Colorado at Colorado State University in sunny and a little toasty Fort Collins, Colorado. Yeah, it is that time of year where the temperatures do get up there. For those of you who are unable to join us today, we're going to record our broadcast for future viewing on our website. And all of our WxTalk webinars are sponsored by grants from the National Science Foundation and donations from listeners like you. Well, during today's webinar, we're going to talk about the weather and climate of the West. Many of you who are with us today either live in the West or maybe have lived there at one time. And I bet you all too well know how weather and climate can vary from season to season throughout parts of the West. Well, we're in for a really great treat today. We have climatologist Nina Oakley. She's with the Western Regional Climate Center located in Reno, Nevada. And Nina has a lot of accolades here. She's got a degree, a bachelor's degree from University of Santa Barbara, California, master's in atmospheric science, University of Nevada, and she is also now working on her doctorate degree also in atmospheric science at University of Nevada in Reno. Nina also completed a teacher education program at the University of Hawaii, Manoa, and spent 5 years as a science teacher in Hawaii and California. Wow, that sounds like a great assignment. Well, a little bit more personal stuff about Nina. She first became interested in weather as a teenager growing up surfing in California. And Nina enjoys backcountry snowboarding, mountain biking, running, cooking, and cloud watching. I bet a bunch of us like to watch clouds. I know I take a lot of pictures myself. Well, welcome, Nina. Thanks for being with us today. It's great to have you on our broadcast.
Yeah, thanks for having me.
So tell us a little bit about surfing in California. What part of California, and what did you enjoy doing that?
So I grew up in Santa Barbara County, California, several different places in the county. And you really have to pay attention to the winds and also the storm systems out in the Pacific that are generating the swells. And so tracking the weather closely really got me interested in going into the field of meteorology and climatology.
That's really neat. I don't think we've had anybody on our show before that's done that, so that's great. Well, listen, why don't you take it away, and we'll join you back with questions from our viewers here after at the end of your broadcast. There we go.
Okay, sounds good. And are we all looking good?
We are. We can see your screen perfect.
Great. Okay. Thanks everyone for tuning in. My name is Nina Oakley. I'm a research climatologist at the Western Regional Climate Center in Reno, Nevada, and I'll be talking with you today about weather and climate in the West. So a little bit about the Western Regional Climate Center and what we do. WRCC is part of the National Oceanic and Atmospheric Administration Regional Climate Center program that consists of 6 different regions. So our area covers the western 11 states, including Alaska and Hawaii. And due to time limitations in this presentation, I'll only be covering the part of our region in the contiguous U.S. The weather of Alaska and Hawaii are fascinating and really warrant a presentation of their own, so perhaps for a future webinar. And so climate services in the U.S. as a whole, the National Centers for Environmental Information handle climate services at the national level, and then we provide a regional focus for the West, and then we work with our state climatologists to provide climate services at the state level. So what we do at the Western Regional Climate Center, we provide access to data for a variety of station networks. This is picture on the right-hand side shows our web pages. We provide support for analysis and interpretation of climate data. We can help people choose what data to use to help solve a particular question. You can email us or give us a call, and you will actually reach a person who will respond fairly quickly. We try and answer requests within a couple days. We do applied research. This is research that has direct outcomes on stakeholders on various topics relevant to the West, such as current drought, El Nino, fire, etc. And we also work with partners at other local, state, and federal agencies and in the private sector to coordinate and support activities related to climate. And later in the presentation, I'll also show you some Western Regional Climate Center tools that may be of interest to you. So a little bit about me. We started in a little bit, but I've been with the Western Regional Climate Center for about 5 years. I've lived in 3 states in our region, California, Nevada, and Hawaii. I love water sports, and now that I live inland, I do a lot of canoe and paddleboard racing and surf whenever I can get to the ocean. And these outdoor activities drive my interest in following the weather. And I'm working on my dissertation studying extreme rainfall and landslides and debris flows in Southern California. So you'll see some bias towards extreme California precipitation in this presentation. So let's start out talking about why is the West unique? Why do we devote an entire CoCoRaHS webinar to looking at the weather and climate of the West? And why do we have a Western-specific regional climate center? So there are several factors that contribute to why the West needs its own focus. The main one is terrain. So this is a terrain map here, and we'll point out some of the main features. These are just general terrain features. I know there's many sub-ranges here, but Rocky Mountains, the basin and range of the Great Basin, Sierra Nevada, Cascades, coast ranges, the transverse ranges of Southern California, and Mogollon Rim in the Arizona area. And so this terrain will greatly impact storms coming through this region and influences the wind patterns and the precipitation patterns and temperature patterns of the West. And we'll talk more about that as we go through the presentation. We've got a cold ocean current running from roughly north to south along our coast, and this has a strong impact on our region. This helps to ameliorate temperatures along the west coast, and we don't have, with this cold ocean, we don't have the evaporation and humidity off of the ocean that you might see along the east coast, where there is the warm Gulf Stream running from roughly south to north. Also, we span quite a bit of latitude in the West. We span about 18 degrees from the subtropics to the temperate mid-latitudes. So in that, down in the southern part of our region, we're in the descending branch of the Hadley cell, so we generally have sinking air over our region and warming and dry conditions. And then when we move up to the Pacific Northwest, we move into a more temperate region where we don't see that that area of descent. So the West is also a place of extremes. Here I have a list from the National Climate Extremes Committee from the National Centers for Environmental Information website. And this committee tracks extremes in the U.S. And of the 16 parameters tracked, I am only showing 10 here for space. 10 of those 16 records are held in the West, in the Western Regional Climate Center region. So, whoops. So folks may think that the weather is fairly unexciting in the West and it's sunny all the time, but hopefully I'll show you here that we have a lot of excitement going on. So all those with check marks next to them, those are all in the West, and the link is at the bottom if you want to take a look for yourself. So in today's talk, we'll start out talking about precipitation, a general climatology of precipitation in the West, rainfall extremes in the West, and snowfall extremes. We'll look at temperature, some of the hot extremes we've had, and cold extremes, and I'll finish up with some Western Regional Climate Center tools you may be interested in using. So, so looking at annual precipitation, for a 30-year average, you can see that precipitation varies wildly across the West. So if you look at if you look at the distribution of colors on this map, with purple being higher 30-year average annual totals and red being lower 30-year average annual totals, you can see that the precipitation distribution is very similar to a terrain map, with the mountains having much higher precipitation than the lower terrain. And we can see that there's sort of a maximum out towards the Pacific Northwest and the Sierra Nevada, since these high mountains in this area generally have first dibs on that moisture coming across the Pacific and with our wintertime storms. Another interesting thing to note is how the areas in the lee, which is generally the eastern side of the mountain ranges, are much drier than areas west of or within the mountains, and this is true for our generally north-south oriented mountain ranges. And then I've also superimposed on here some of the very high totals that we see. Up in Quileute, Washington, just over 101 inches is their 30-year average. That's the 1981 to 2010 average, and this is listed as the second highest long-term average annual total, just behind Mount Washington in New Hampshire. And then down in the southwest, in very stark contrast, we have Yuma, Arizona, with an average annual precipitation of 3.3 inches, which is the driest of long record stations in the U.S. And one other cool thing I like to point out on this map is in the across the Great Basin, you see all these lines of green. Those are the many mountain ranges of the Great Basin. We have 150 named mountain ranges in Nevada. So look, a more detailed look at what I talked about the lee side of the mountains being dry. Assuming this is a cross-section of a north-south oriented mountain range, you have, as the storms come in, most of the moisture in a storm is contained in the lowest, approximately 3,000 feet, lowest 1 kilometer of the atmosphere. And so as that storm and its relatively warm, moist air comes in off of the Pacific, that moisture is forced upward by the winds and by the mountain barrier, and as that moist air moves upward, you have expansion of the air and cooling as it moves into higher levels of the atmosphere, and you tend to get most of your precipitation on the western slope of the mountain range, with a maximum usually just west of the crest. And then on the other side of the mountain, now you've spent out much of that moisture, and then as the air moves over the mountain and descends, it's going to compress and warm, and you have evaporation of that moisture, and so you end up with a rain shadow on the lee side of the mountains. So let's break out that annual precipitation into seasons. So now we're looking at the fraction of annual precipitation received in the October through March period. This is what we typically call the cool season in the West. And you can see that during this period, California, Western Oregon, and Washington received most of their precipitation, with most of this area being roughly 70 to 90% of annual precipitation occurring during this October through March period. And you can see, if you look close, that, that the San Francisco Bay Area and parts of Los Angeles are receiving over 90% of their precipitation in the cool season months. And this is due to the fact that the West Coast precipitation is dominated by wintertime mid-latitude cyclones, a fancy name for storms. And these storms form in the western or central Pacific, or sometimes in the Gulf of Alaska, and either track eastward or from north to south. And sometimes unimpeded for thousands of miles. They encounter that complex terrain along the west coast, and you have orographic forcing, or forcing by other mechanisms, sometimes along a cold front, and you can get your wintertime precipitation here. And then you can see, as you move eastward, we see decreasing fraction of precipitation attributed to the cool season. And there are other processes that we'll talk about that dominate over this area in other parts of the year, but we do get some moisture that can get around these mountain barriers into this area, or sometimes we have storms that, that may come down through this area and kind of skip the mountains altogether, and we'll talk about those a little more. And then if we move to the April through June period, now you can see that the largest fraction of precipitation received by an area during this period lies mainly east of the Rockies, in eastern Montana and eastern Wyoming. And so by this part of the year, we've had the subtropical high start to build back over the northeastern Pacific, keeping our storm track higher up and keeping storms out of off of the west coast. And then we've seen a decrease in storm frequency there, lowering their percent of normal precipitation. Temperatures are climbing over land, and the surface is warming, but the air aloft is still very cold, making the atmosphere very unstable over this area and favoring thunderstorms if we can get moisture off the plains and off the Gulf. So we develop thunderstorms in this area, and this contributes roughly half of eastern Montana and Wyoming's annual precipitation. And I won't go into too much detail about these plains thunderstorms, as Natalie from High Plains covered plains thunderstorms in her talk last month. And some of this thunderstorm activity and moisture can make its way further west, leading to some of those yellows and greens you see over the inland northwest and the Great Basin. And this season's also the time when cutoff lows, which are a slow-moving cyclone that's detached from the jet stream, and these tend to form in place over the west out of a breaking atmospheric wave, or sometimes they track on shore and form off the coast and track on shore. And these can provide prolonged showery conditions over the west. So we'll take a more detailed look at that cutoff low situation. So here's an example from May 6th. And so we have a cutoff low forming over the west here. And so we can see these by looking at the 500 millibar height field in a weather forecast map. And you're looking for basically these concentric circles around a central low pressure point. And then the wind flows roughly parallel to these isobars, to these lines, or iso heights. And so you end up with counterclockwise flow around this low. And as you can see, if you have the easterly flow coming around this low, you're going to get easterly flow up what's usually the lee of the Sierra Nevada, and now you have upslope flow in the lee of the Sierra Nevada, and so you're going to get, it's going to become the windward side, and you can get orographic precipitation in the lee of the Sierra. And as you can see, during the month of May, we had unusually high precipitation associated with several of these cutoff low systems. We saw about 150 to 400% of normal precipitation in the lee of the Sierra. So these lows are typically removed from the mean westerly jet stream, which would be roughly up here, and they can meander and create prolonged precipitation until they're swept back up into the jet stream. So moving on to the July and August season, this is when we see the North American monsoon dominate over the southwest, and as you can see, southern Arizona and eastern New Mexico are really the kind of the core area of this monsoon feature, and get 30 to 50% of their precipitation during July and August. But monsoon-related precipitation can extend northward into the Great Basin and into the Rocky Mountain states as well. And we'll talk about the North American monsoon a little later. So, so now that I've walked you through this, and you're all experts on the seasonal distribution of precipitation, we have a little game to guess which monthly rainfall graph goes with which. So I've given you 3 graphs here of monthly distribution of precipitation and 3 locations within the West. So take a second and see if you can pair up in your mind at home which location goes with which graph, and then we'll walk through it really quick. So the top graph, we see that most of the precipitation is occurring through the October through March season. That's going to correspond with Blue Canyon, California, in the on the western slope of the Sierra Nevada, where those mid-latitude cyclones dominate. And then second, we see that the April, May, June period dominates, and that corresponds with Billings in eastern Montana. And then, of course, when we see July and August have the most precipitation, that will correspond to Tucson, Arizona, where the monsoon dominates. So we can take a look at how this precipitation arrives. So does it occur over many days in the season, just a few days in the season? And so over the southwestern U.S., generally it takes roughly 5 to 10 days to get 50% of annual precipitation. So there's not a whole lot of rainy days that we have to collect our annual precipitation. When we move into the Pacific Northwest, it's often 15 or more days to get 50% of the annual precipitation. So a lot more rainy days, more opportunities to collect your precipitation total. So over much of the West, especially the Southwest and California, the arrival or failure to arrive of just a few storms can really make or break the annual total. So if we miss out on just a few storms in California and Nevada, that can put us into drought. So it makes drought a frequent thing in our region, since we're so dependent on getting enough storm activity to get our precipitation days. So very often this precipitation will come in the form of extremes. So, so on this map here, we're looking at stations that sometime in their record had a maximum 3-day precipitation total exceeding one of 4 different thresholds. They're in millimeters right here, so they're rounded to nice clean numbers, and I've converted them to inches as well. So, so what you'll notice is that areas in the mountains of California, in the Coast Range, in the Sierra Nevada, and in the transverse ranges see 3-day precipitation events on par with the southeastern U.S., areas that experience hurricanes and intense thunderstorms. So the feature generally responsible for these high storm totals along the West Coast is a feature called an atmospheric river, and we'll talk about them over the next few slides. But the main thing I want to point out here is, people think most of the extreme precipitation is happening sort of in this region, over Texas, over Florida, over the Gulf states, but we see precipitation extremes of the same magnitude in California and up into the Pacific Northwest. So here's a breakdown of generally which sort of feature is responsible for extreme precipitation, and in some cases flooding in the West. And there's some overlap and variations to this, so this is just giving a broad brush view. And so we see that atmospheric rivers generally affect the coastal states. It can reach inland a bit, but it's hard for moisture to penetrate past the mountain ranges. And there are a few favorite pathways I'll show you in a couple slides. And then over the Four Corners states and parts of eastern Nevada, these experience the North American monsoon, which can create extreme precipitation in that area. And though in some cases and under the right conditions, you can have that monsoon moisture extend further northward. And then east of the Rockies, we see generally spring and summer thunderstorms dominate for some of their precipitation extremes. And again, we're going to mainly steer clear of that and focus on the southwest monsoon and on atmospheric rivers. So what are these atmospheric rivers? There's an atmospheric river in this picture right here. This is a satellite image of integrated water vapor. So this is how much water vapor is in the vertical column of the atmosphere. And so these atmospheric rivers are these narrow corridors of high water vapor transport, and they move water from the tropics where lots of water vapor is present. You can see the tropics and their high water vapor are represented by these red to orange colors, and the atmospheric river moves some of this tropical water vapor up to the mid-latitudes where it tends to be much drier, as you can see with these brown and purple colors. And so you may have heard of certain flavors of atmospheric rivers, such as the Pineapple Express. I would call this event a Pineapple Express, an atmospheric river originating near Hawaii. Or there's also the Mango Express, which tracks back all the way to the Philippines. And we tend to see about 10 to 20 atmospheric river events hitting the coast each year. And these may vary in strength, so they're not all generating extreme precipitation, but some do. And there's high variability of where they hit. Each one doesn't always hit everywhere on the coast. And let's see. And so one interesting thing about an atmospheric river is that most of the moisture is located in the lowest, roughly a kilometer or 3,000 feet in the atmosphere. So if you think back to our terrain map, and I talked about this a little bit earlier, as the atmospheric river moves across the Pacific and encounters this elevated terrain when making landfall along California, Oregon, or Washington, that low-level moist air is forced upward, cools, and can produce ample precipitation. And when conditions are right, this precipitation can generate intense flooding over the area. And so this snapshot here of the integrated water vapor is from December 11th, 2014. So we'll take a look at what the atmospheric river did in terms of impacts. So most cool season flooding events tend to be associated with these atmospheric rivers. And so here's an example of the damage associated with the atmospheric river. So when this made landfall in California, we had flooding in Healdsburg in Northern California. You can see some folks kayaking down the streets of Healdsburg. And looking at a CoCoRaHS gauge observation for that day, for December 11th, this observer saw 5.88 inches, and that was the wettest day in that station's 6-year record. The atmospheric rivers, sometimes they'll sort of spray down the coast like a fire hose, and so this one hit Northern California and then traveled and impacted Southern California as well. So one of the impacts we had was there had been a recent fire near Camarillo, California, so very close to Ventura, California, and there was a fire, a burn area, and we had heavy precipitation on that burn area, and which generated a debris flow and buried some houses up to their eaves. And compared to the precipitation received in Healdsburg, the precipitation totals weren't as high. In Southern California, our observers down there recorded just over 2 inches for December 12th. But this precipitation came in very intense amounts. We saw rain rates with this storm of nearly 1 inch in 15 minutes. So so very, very high rain rates that helped to initiate this debris flow. So, so when we look at how atmospheric rivers affect the West in terms of season, we can see that atmospheric rivers, storms with atmospheric rivers, provide a large fraction of cool season precipitation for coastal California and Oregon and Washington. And then there are a few pathways. There are a few pathways for moisture to penetrate inland. Namely around the southern end of the Sierra Nevada and around the northern end of the Sierra Nevada and up the Columbia River Valley. And so we see a decrease from west to east generally in atmospheric river fraction of cool season precipitation associated with atmospheric rivers. One neat thing to note here is the highest area of the Sierra Nevada is in this region right here. And so you can see that's where the greatest rain shadow of atmospheric river precipitation lies, is just in the lee of the Sierra Nevada there. And so, so conclude with atmospheric rivers and move on to the North American monsoon. So complicated graphic here. To put it simply, what happens with the North American monsoon in just a sentence, it's during the summertime we see a shift in the position of atmospheric features that allows moisture from the Gulfs of California and Mexico, and also the Sierra Madre, the tropical eastern Pacific, to move into the southwest and promote thunderstorm development. And then the more detailed description, the North American monsoon begins roughly in May in northern Mexico as solar radiation increases as we move into the late spring and summer season. And the land heats faster than the sea, and this helps to draw moist air up over the land. You have precipitation over the Sierra Madre of northern Mexico. And you have vegetation grow, evapotranspiration occurs, and this moistens up the atmosphere and cools the atmosphere over the Sierra Madre. And then as we move into that June-July season, New Mexico and Arizona start heating up, and a gradient develops between the cooler moist air over northern Mexico and the hot, dry air over the desert southwest. And so as the desert is heated, the air rises, and we tend to form a thermal low over the southwest here at the surface. So we have an area of low pressure, and this rising air and low pressure sort of acts as sort of a generating a vacuum to help draw in moist air at lower levels from the Gulf of California, the Gulf of Mexico, tropical eastern Pacific, and that moisture off of the Sierra Madre and even the southern plains in some cases. And then in June and July, at upper levels in the atmosphere, up at say 30,000 feet, the winds tend to, as the Four Corners High sort of shifts location, we have winds shift from the generally westerly flow that we see at other points in the year to a somewhat easterly flow as it wraps around this high pressure system. And this further facilitates moisture transport into this area. And a monsoon in general, by definition, is a seasonal shift in winds. So this is where we get the term monsoon for this phenomena, though you'll hear some folks debate over whether the North American monsoon is a true monsoon as compared to, say, the Asian monsoon. And as this moisture, by the changing position of the atmospheric features, as this moisture encounters terrain or and the hot surface over the southwestern U.S., the moisture is forced upward, generating thunderstorms. And so several metrics exist to describe when the monsoon actually begins and ends, but currently June 15th through September 30th has been designated as the monsoon season, during which monsoon-related thunderstorms are likely to occur. However, the monsoon is not consistent through this season. You may have extended periods of monsoon breaks. And then finally, by fall, the temperature contrast between land and sea is reduced as days begin to shorten. And the monsoon season ends, we go back to generally westerly flow over the southwestern U.S. So if we look at some examples of monsoon impacts and monsoon flooding, extreme precipitation, here's an example from last year. We had flash flooding in Las Vegas on July 6th. And the precipitation with the summertime monsoon can be very highly variable in space. This is one reason CoCoRaHS observations are very important. So the highest I could find associated with this event was just over ½ an inch. And this precipitation may come in short bursts, and this storm in particular was highly variable. I think there were totals over an inch at some non-CoCoRaHS gauges for this storm. But having the CoCoRaHS observations to add to the other observations really gives us an idea of the spatial variability of these thunderstorms and where the most rainfall fell, where it didn't fall, and then we can look into that as meteorologists to understand some of the dynamics of the storm. Another impact of these monsoon-related thunderstorms is we can get these dust storms or haboobs that form from the outflow out of these thunderstorms. And so the thunderstorm will have these strong winds that will come downward out of the thunderstorm, and these can loft dust hundreds of feet into the air and create these dust fronts that often cause car crashes and limit visibility and reduce air quality. And we tend to see roughly 1 to 3 of these haboobs per year in Arizona. So hurricanes, do we have hurricanes in the West? We talked about atmospheric rivers and their extremes. We talked about the North American monsoon, flooding associated with that. Do we have to worry about hurricanes, tropical cyclones in the Southwest? The answer is kind of. So we don't often see the hurricanes themselves move into the western U.S., but they often, as they're dying, the remnants will move into the west. So most hurricanes are going to sort of lose their pizzazz as they move over the cooler waters off the coast of northern Baja and into Southern California. And so by the time they get to 30 degrees north, they're really dying out. And however, we do see that when these tropical cyclones are dying, if the large-scale atmospheric flow is favorable, it can suck up their remnants over the southwestern U.S. and sweep them sometimes even further north over the Great Basin and into the southern part of the inland Northwest in some cases. And so this typically happens in late summer or fall, September, October, though the season extends roughly, the hurricane season for the Eastern Pacific extends roughly from mid-May to November. And these cyclone remnants will tend to lead to humid conditions where it's normally arid in the late summer, early fall, say over coastal Southern California. We'll see very humid conditions. And as when this moist air moves over the warm surface in this late summer, early fall period, you can get thunderstorms develop. And these can be especially intense if we have a low pressure system move over the region, as can happen in late September, early October, and that can interact with the warm surface and that tropical moisture to produce some very strong thunderstorms. So taking a look at one of these in particular, some of you may recall that last September we had the remnants of Hurricane Linda. This is its track right here. We had the remnants of Hurricane Linda move into the southwestern U.S. There was a low pressure system that helped to move some of it into our region. And so we had flash flooding in southern Utah, and 13 were killed when they were driving across a wash, and we had flash flooding come through this wash, and they drove into it and were swept away. And then nearby in Zion National Park, there were hikers hiking through a narrow canyon. They had set out in the morning, and the sky looked clear, but these thunderstorms developed in the afternoon associated with the remnants of Hurricane Linda. And so a total of 20 deaths in southern Utah associated with this dying hurricane event. And so again, I've got an observation from CoCoRaHS Observer here in Springdale in this area, and they saw just over an inch. That probably came in a very short period of time. So again, these CoCoRaHS observations are really helpful in us to understand the spatial variability of these thunderstorms. And also I think CoCoRaHS observers in general are more weather-wise and can help keep other folks safe by being keyed into the potential dangers of flash flooding, being aware of precipitation patterns in their region, and keeping in tune with the forecasts, watches, and warnings issued by their local weather service offices. So moving into snow, snowpack is extremely important in the West for a variety of reasons. Snowpack really drives much of our water resources and ecosystems. And spring and summer snowmelt runs off into rivers and streams, filling our reservoirs and providing water resources for the people and the critters and the agriculture and the vegetation in our region. So low snowpack years can have huge implications for water resources, as we've seen with the ongoing California and Nevada drought over the last 5 years. So reservoirs act as a flood control mechanism in the winter, and then as storage for water resources in the summertime. So if snowmelt is not available to fill the reservoirs in the spring and summertime after they've been kept low to act as flood control in the winter, water resources start to become depleted, as they have over the last several years, though we have seen some Northern California reservoirs come back up with our roughly 85% of normal snowpack in the Sierra this year. And low snowpack has implications for the critters of our region too. Fish really need cold waters throughout the summertime, and if there is low stream flow from lack of snowmelt and temperatures rise later in the summer as snowmelt decreases and streams warm up, this can be very damaging to fisheries. And so this image shows snow across the western U.S. on February 7th of this year, and so you can see our main features standing out, the Cascades in the Pacific Northwest, Sierra and Nevada, snowpack here. There is Lake Tahoe and Pyramid Lake to give you some frame of reference. And then over the Basin and Range of Nevada, there's the Great Salt Lake here, Uinta and Wasatch Mountains of Utah, and then Rocky Mountains. So you can see our areas that tend to collect snow in this region. And so for fun, some western snow extremes. So the highest snow depth, this is like a one-day snow depth measurement, just as you folks would make in your CoCoRaHS measurements of snow depth. So the highest recorded in the West is at Tamarack, California on New Year's Day, 1911. And they recorded 451 inches in depth of snow. And this was an interesting year. Apparently New Year's Day of 1911 had started out relatively snow-free in passes. There hadn't been many storms to start off the late 1910 year. And so folks thought they were setting up for a relatively mild winter. But storms began roaring in mid-January with several large storms dumping lots of snow, and then as we moved towards the end of the season, they saw this record March snow depth observed. And then looking at our highest 24-hour snowfall totals, the record goes to Silver Lake, Colorado, which is slightly outside of our region, but we're number 2 for in the U.S. for highest 24-hour snowfall at Echo Lake in the Sierra Nevada, which is just slightly north of Tamarack, and they had 67 inches fall on January 5th, 1982. So let's talk about move from snow to heat. Logical transition. So looking at extreme temperatures, we in the West hold the world high temperature record on Earth of 134 Fahrenheit recorded on July 10th, 1913 in Death Valley, California. That's a picture of the Cooperative Observer Station where that record was made, and the location of Death Valley. So a general recipe for extreme heat, and this doesn't always apply, there's certainly exceptions to this rule, but generally you want to be at low elevation. Death Valley is, I think, somewhat more than 200 feet below sea level, and this allows for maximum sinking and compression and warming of air. You want to be generally far from the ocean, especially a cool ocean like we have off the coast of California, as the ocean temperatures will help ameliorate the air temperature and won't let it get as hot. You want to have a strong high pressure ridge overhead such that you have sinking air and dry conditions, and those will get you to an extreme high temperature. And one interesting thing about there's a story to every temperature extreme and every climate extreme, really. So this had this temperature record had been in contention with a record at, probably pronouncing it wrong, but El Aziza, Libya, which was recorded on September 13th, 1922. And in 2012, the World Meteorological Organization conducted a study into whether that temperature in Libya was viable. That record was 136 Fahrenheit. And after doing an inquiry into that Libya temperature record, they found some evidence that it may have been an error, and that that temperature was removed as the record, and the 134 at Death Valley took the record. So we had some of these conditions this past week, this Monday. We had a very strong high pressure ridge. This is 500 millibar heights, and this is showing the height anomaly in the colors. So the redder colors indicate stronger, more anomalous high pressure. And so we saw Phoenix, Arizona hit 116 Fahrenheit. Blythe, California set an all-time record for that station's record that began in 1948 at 124. And Death Valley hit 126, still far off that world record, but a tie for the third warmest June temperature on record. So on the opposite end of that, looking at what drives cold extremes. So our coldest temperature record in the conterminous U.S. is -70 Fahrenheit at Rogers Pass in west central Montana in January 1954. And so there's, of course, a story with this extreme as well. As the story goes, dictated to me by our regional climatologist, Kelly Redmond. So the observer for the station knew it was very cold outside and went out to make his measurement. And the mercury was so low in the thermometer it was very hard to read. So he went back and got a magnifying glass and a file and etched where the mercury level was, and then consulted with the local National Weather Service office. And in the account of this observation, when making the reading, he was very careful to breathe out of the corner of his mouth so that he wouldn't influence the measurement and change the thermometer at all. So it was very, very carefully done. And that etched thermometer ended up being sent to Boulder for some lab testing to see if they could reproduce that temperature and level in the thermometer. And after this careful study, the temperature was indeed verified. But if we look at the recipe for cold extremes, this wouldn't be the place you necessarily expect it to occur. So you do want to be at sort of a higher latitude, so you have short winter days, not a lot of solar insolation. You're typically going to have these cold extremes following a cold front, so you typically have wind associated with a cold front, and then it's going to be calm and cold after that cold front passage when you move into the cold part of the storm. Fresh snow can help for building a cold extreme that will reflect the incoming solar radiation and also won't let the ground heat up and emit any heat. Elevation, so your coolest places tend to be elevated valleys where you have the air at the mountaintops cooling and sinking down. That cold, dense air sinks into the valleys and pools into the valleys. This can cause those nasty temperature inversions we see in some locations in the Great Basin that trap pollutants in that cold, dense air layer. You're going to tend to have your cold extremes far from large bodies of water, which can, if they're not frozen over, which can ameliorate the temperature. And you want to have dry air, low humidity, so you can effectively radiate your heat away at night. And so this Rogers Pass location is not in an elevated valley. It's a pass, and but it is sort of a rolly terrain, so there may have been some microscale cold air cooling associated with that. So one takeaway from this is when we're talking about records and extremes and trying to define the extremes in our country and on Earth, it's really important that we have these very carefully made, considered observations. So, and I know you all, as CoCoRaHS observers, are keeping that in mind. And so we'll wrap up with talking about some Western Regional Climate Center tools that you can use. First tool I'll share is, and we have many, I'm just giving a sample of a few of them for time. First one is the West-Wide Drought Tracker. This allows you to generate maps and data for temperature and precipitation and drought indicators based off the PRISM data set. It's a 4-kilometer temperature and precipitation data set. Here's an example of one of the maps for the Palmer Drought Severity Index that you can generate from the West-Wide Drought Tracker. This is on a monthly basis. It updates around by the 5th of every month. And there's the web address there. Another tool that we've been working on, and it's up and running, is called Scenic, the Southwest Climate Environmental Information Collaborative. This was developed by Britta Dauder here in our office with the Southwest Climate Science Center. And this provides a variety of tools to analyze, access data, and to make charts and tables. This works off the Applied Climate Information System, which has CoCoRaHS stations in it. I've shown you we have a station finder tool on this page, and I've shown you a map here, and you can click this to show CoCoRaHS stations on our station finder, and you can perform a variety of analysis for your station or other stations in your region. And then we also have a variety of real-time weather stations, and you can get graphics like these that are a 24-hour graphic with the maxes and minimums associated with the day. This is for a few days ago at the station at our office. And some of these are in remote locations, so if you have a location you'd like to go to and you didn't know if there was a weather station there, we might have one near there. You can check in on that, and two of these stations two of the pages that have some of these stations on them are listed right here. So last thing is, how does Western Regional Climate Center use CoCoRaHS data? As I mentioned a couple times in our presentation, we fill in data gaps in storm events. Sometimes we're helping people who are looking for data associated with a particular event, and when we don't have official recording stations at a precise location, we can use CoCoRaHS to help fill in the gap and understand where precipitation did and didn't occur within a storm. We can check validity of observations. Sometimes our remote stations may have glitches in them, but it's hard to tell if that glitch, what we think is a glitch, is real or not. And so CoCoRaHS stations can help us verify those observations. again, very helpful in understanding the spatial variability of precipitation in a climatological sense, and also in a storm, at the storm level. And we're also really interested, especially in the Great Basin, where observations are lacking, in using CoCoRaHS to help drought monitoring and understanding rangeland conditions in the region. And we're hoping to move towards making more use of the drought reporting in CoCoRaHS. And one thing to note is, as your records become longer, they become more valuable to us. So please do your best to keep your record consistent and keep at it. I know it's tough. This is our Western Regional Climate Center gauge. We have one here. I have one in my backyard as well. We have a nicer view from ours than you do than I do at my house. This is Mount Rose up in the background here, and that is all. So thank you for listening, and thank you for being a CoCoRaHS observer. And I'll leave you with some lenticular clouds in the lee of the Sierra Nevada. We didn't get into talking about clouds and winds today, but that would be its own, it could be its own separate presentation. So thank you all so much.
Thank you, Nina. Really appreciate great presentation. Maybe you can come back later in the year and do it on Alaska and Hawaii, if we could put that in there somewhere in the future, if you're interested. I'm sure folks might be interested in that.
Yeah.
And so we'll have all the different URLs and resources later next week posted on our website that Nina has given us. We'll also have a copy of her PowerPoint presentation, which you just saw, and then the recording of today's presentation. Very informative, a lot of interesting things to touch upon. We do have also some previous CoCoRaHS webinars, one on atmospheric rivers by Marty Ralph from the Scripps Institute, and he talked about those. Nina touched on those today. You know, you also get those on the East Coast. If you remember the South Carolina event, just with Hurricane Joaquin going off the coast, that atmospheric river bringing, so it's not only in the west that you experience this stuff. And then another one we did last year on the southwest monsoon. So a lot of good stuff related back and forth as climate touches on all these different things. So if you've got time, you know, we can take a couple questions from our listeners out there, and let's see what we've got here already. Here's one from Jennifer in Northwest Washington. She says, we seem to be having more air inversions in the winter that last longer. Why is this? So that was her question.
Yeah, so I would say that your inversions tend to occur under a high pressure ridge, and when you have very calm conditions where the air can pool. I don't know. I haven't looked into whether there's been a trend in more, but in under drought conditions, and I believe the Pacific Northwest was had been dry last year. So this year they're doing a little bit better, but we did have fairly dry conditions over much of the Southwest and Great Basin, so that would be consistent with more frequent high-pressure ridging, which is going to promote that sort of stale air and clear skies that are going to let the heat radiate away readily and allow cold air pooling to occur. So, so I would expect that when you're observing dry conditions and very few storms in the wintertime, you're going to tend to have more frequent inversions.
Okay, thanks. If anyone else has a question, go ahead and type it in. Include your name and your state that you're listening from. Really interesting stuff. So the El Nino last year, really much of a dent has it put in the drought out there? You may have touched upon that earlier.
Yeah. So the typical pattern that we think of associated with an El Nino event, the typical precipitation pattern that we think of is generally drier than normal up in the Pacific Northwest and wetter than normal across Southern California and into Arizona. And we really didn't see that pattern this year, which has raised a lot of questions for meteorologists and climatologists as to why didn't we see what we expected that's similar to what we saw in the other large El Nino events like 1997-98 and 1982-83. But when you look at the sort of spread of these moderate to strong El Nino events, not all of them really closely follow that precipitation pattern of dry in the northwest, wet in the southwest. There is some variability, and then we also have some variability in the El Nino conditions in the eastern tropical Pacific themselves, where sometimes you have that area of warm water lying right off the coast of Peru, really far west in the Pacific, and then sometimes you have more of a central Pacific El Nino, where that area of warm water is more concentrated in the central Pacific, which we saw this year. So there's a lot of variables that go into that, and the position of the warm water in the tropical Pacific can really impact what kind of storm track pattern we end up seeing along the west coast. So there's been a lot of variability in the past, and then with the sea surface temperature patterns in the Pacific, that may have had an influence on it as well. And we did get some decent precipitation in the California and about Northern California region, and we were around 85%, 84% of normal snowpack for this year in the Sierra Nevada. And so it did help a little bit to ameliorate the drought slightly. We did see some reservoirs in Northern California fill up a bit, but really we have this 5 years of accumulation of drought conditions, and so while you may fill up your reservoirs, you still have all these impacts of the for example, the trees in the central and southern Sierra Nevada were drought stressed and then were attacked by bark beetles, and so we've seen a massive tree die-off, and that can't be ameliorated by one sort of a moderate winter. So really we're so deep in drought. Some of the factors may improve within 1 year, but groundwater replenishment, some of the landscape issues, it takes a lot longer than that to work our way out of that. And our reservoirs in Southern California are still looking pretty bad.
Okay, we've got a couple questions coming in and a couple of prediction ones. So here are two questions. I'm going to, on prediction, give them to you together. So Mark in New Mexico wants to know if any prediction on the North American monsoon for this year. That's the first one. Jennifer wants to know, will La Nina bring colder temperatures this winter in the Northwest? So one on the monsoon and the other one on La Nina's effect on the temperatures in the Northwest.
Sure. So monsoon, it's notoriously hard to predict what it's going to do. It's pretty well known that monsoon predictions are don't always verify, but the latest CPC, the Climate Prediction Center outlook, has shows, remembering off the top of my head, for western Arizona, things were tilting slightly toward, they were saying there's a slight chance that we might have monsoon related precipitation for the July, August, September period in that western Arizona area, tilting the odds towards above normal, and then CPC was calling for equal chances of above or below normal monsoon precipitation elsewhere. So they weren't really seeing a strong reason to believe it would be above or below normal with any confidence. So you can check out the, if you look at the CPC Climate Prediction Center June, July, August, or 1 month outlooks, they'll give you more information on that. With La Nina, the pattern there is often the reverse of the El Nino precipitation pattern. It's generally favored to be wetter and slightly cooler than normal in the Pacific Northwest, and then drier across the Southwest. But as we saw this year, really we can use that as a general guideline, but the atmosphere doesn't always follow that. Follow those guidelines. So it's still, we're really early in the season for really getting a handle on what the forecast will be for the coming winter. It sort of firms up as you move into the fall. We can say a little bit more. So again, I wouldn't necessarily count on La Nina bringing cooler and wetter conditions to the Pacific Northwest. It's been an odd year, couple of years up there. They've seen some very warm temperatures, some very wet conditions. So we'll have to wait and see what the forecasts say for that as we move into the late summer and fall season.
Okay, here's one from Paul across. He's on the Front Range of Colorado. He's an avid gardener, and he's been a CoCoRaHS volunteer for 18 years now, since its inception. On the Front Range, there's been a shift in seasons toward an earlier spring and a later fall. He wants to know if this is occurring across parts of the West as well.
Yes, so we saw this year our snowmelt. We had a very warm April, and also part of March was quite warm in the West, in the Sierra Nevada Cascades. And so we saw a really early and quite rapid snowmelt early in the spring season. Usually we see that the peak in the snowmelt was roughly 2 to 3 weeks earlier than normal this year, and this kind of raised some concerns for that spring runoff that I talked about in the presentation, that if it runs off too early, it can have some impacts on ecology in the region. And then later fall, not sure how to address that. It's been my experience living in the West that it's just highly variable when we kind of transition into that fall storm season. Sometimes it'll come as early as late September, sometimes October, sometimes not even till November. So I don't know if I could say anything certainly about the late fall, but definitely we're seeing some of that earlier spring warmth and earlier snowmelt here.
Okay, and it looks like we got the final question of today. Jessica writing in from Maryland. She wants to know if do you believe the warm blob of ocean temperatures off the coast of California contributed or was the catalyst to the extreme drought conditions witnessed in California 13 through 15?
So the blob, the explanation that I've heard that seems to resonate with me the most is not that the blob caused the persistent high pressure ridge over the West that was associated with the drought, but rather the formation of the persistent high pressure ridge caused the blob to form. So the blob being a byproduct of that high pressure ridge. So when you have a large dome of high pressure over the eastern Pacific there, you don't have, it's very calm, tends to be very calm under the ridge, very clear. So you have sun beating down on that ocean water and warming that ocean surface water, and then you also have very little winds to help mix that ocean water. And so you end up generating these very warm sea surface temperatures under that ridge. And then you definitely have feedbacks from that'll further alter the weather patterns. But really the blob is sort of, the two are intermixed. But yeah, certainly after you develop those sea surface temperature anomalies, it continues to perturb the atmosphere and wave patterns that storm tracked by having that high that sea surface temperature anomaly.
Henry, can I ask a question?
Oh, Nolan's with us. Hey, Nolan, great to have you here today. I knew you might be lurking in the background, and yeah, it's great. Good to have you on.
Nina, I believe there was a day, maybe even more than one day this winter, when Reno was the wettest place in the country based on CoCoRaHS data. Do you recall this event? And I believe there was a cutoff low associated with it.
Yeah.
What are your recollections?
Whoops, let me see if I can get my slideshow to go back up. Yeah, I had one of those. Let's see how long it takes to move through. But yeah, we had quite a few cutoff lows, and I wanted to run, there we go. Here's one in May where you can see that Reno is at the southern end of Washoe County here, so you can see Reno being quite wetter than normal in May. So I'm guessing that was either a May or possibly a June date. But yeah, we had quite a few of these cutoff low pressure systems over this April, May, and June period. I would venture to guess it's one of the most frequent cutoff low seasons since 1948, where I have records for, but I haven't had a chance to run it through any algorithm yet to determine if that is in fact correct. But quite a few of these cutoff low events, and creating that upslope flow in the eastern Sierra Nevada, and making Reno and areas down here. We saw some records set at Bodie and Bishop, California as well, for precipitation associated with these cutoff lows.
And I think May of 2015 also had some pretty good gradients where most of California was just baking hot and dry, and yet there was surprising amounts of precip on the east side of the Sierra. It's just fascinating to see that you can get wet under just the right situation, even in the lee of that water harvesting mountain range that usually keeps you so dry. And what's the Reno average annual precip, by the way?
We are about 9 inches annually. Yeah. So yeah, some of these lows brought us I don't know about a tenth or more, 20% of our annual precipitation when we got a couple inches out of these. So yeah, it's been quite an interesting spring, and very similar to last spring. If you look at for the Great Basin, for the sort of western northern Great Basin, we've been seeing up until recently greenness. If we look at greenness computed from satellite imagery, we've been around 200% of average greenness. So it's been very green here, but as we've dried out over the last couple weeks, it's looking quite brown out there now, and we've had a couple small fires in the area recently.
So wet springs can actually bode badly for wildfire season.
Exactly. If we have a wet spring in the Great Basin and we grow lots of vegetation, and then it quickly dries out, and then we get our afternoon Washoe zephyrs form as we have a temperature gradient, pressure gradient between Sacramento and Reno, we get these strong westerly winds down the mountain, and those can fan up any fires that start. So yeah, it could be an interesting fire season in this area.
Thanks so much for being our webinar this time around. We appreciate it a lot.
Yeah, great. Thank you for having me.
Yeah, it's great to have you. You know, we got a couple other questions. We're going to take those off the air, and Nina will follow up with you through email in the next week or so on those. Nina, thank you again. Great presentation. Just learning a lot. And for you folks out there on the survey at the end, if you're enjoying this series we're doing on the different climates of the country, let us know that. Let us know what you think about that. We're about halfway through now, so we've looked at the Midwest, we've looked at the Great Plains, We've looked at the west, and you know what's coming up next? Thursday, July 14th. Now, if any of you historians know what that date is, and if you're from France, you'll recognize that's Bastille Day. And so coming up on Bastille Day, we're going to look at the southeastern U.S. Chip Conrad of the Southeast Regional Climate Center. He'll be presenting on the climate and weather of the Southeast. So don't forget to sign up. We'll have the link up there shortly for doing that. And then as you leave today, again, our survey that's out there, we really appreciate you doing that. So again, Nina, thank you for being with us, and we hope to see you again real soon as we go to these different meetings and talk to you. And again, thank you folks for being CoCoRaHS volunteers. You could hear what Nina had to say, how important your volunteer observations are, and that really makes a difference. Well, until mid-July, there on Bastille Day, this is Henry Regis for the rest of the CoCoRaHS headquarters team saying goodbye and have a great afternoon.